Advanced Math Honors. We are done with theorems, yay! But we still have one more day to talk about these polynomial roots, because I want to take a microscope and I want to zoom in on complex roots, simply because I feel like they're kind of we know how to factor, and then we factor and we get complex roots, and we're kind of like, oh, I did something wrong. Or we know how to do all of these things, but then we get complex roots, and we're like, oh, wait, what? So we're going to look at just complex roots, and we're going to talk about them. All of these examples that I'm going to go through are from page 146 and 147 and 148 in your textbook. So if you don't understand this video or you don't like looking at my notes page, go look at the book to follow along. So what I'm gonna what the whole process of what we're gonna be doing is we're just gonna be looking at polynomials and looking at their complex roots. So the first thing I want to say is write this function as a product of complex linear factors. So here's my function. It's a quadratic function. I know it's going to have two roots. I want to rewrite them as their linear factors, so I'm going to find the roots and then I'm going to put them back in parentheses with the x's. So I have that. I go here by subtracting 5 from both sides. I take the square root of both sides, get plus or minus the square root of negative 5, and then I get two distinct roots, I5 and negative I5, because under the radical, if we have a negative, that doesn't exist. Let's remember our parent function of the square root of x, and that will tell us why it doesn't exist. Our parent function, it all comes full circle, guys. Everything in math does. Our parent function for that's way too low. Okay, our parent function for the square root of x looks like what? That was square root of x. So what do we have square root of negative 5? Where would square root of negative 5 be? At negative 5. Where's the graph? It does not exist. So it doesn't exist, so it's imaginary. All comes full circle, don't it? Ain't that neat? Okay, so we put it back and we rewrote it in linear factors. This is an example of one linear factor, two linear factors. Linear factorization theorem tells us that with the fundamental theorem of algebra, tells us that these two factors are both roots, and we have exactly two linear factors because we have exactly two roots because the degree is 2. So everything's good in our world there. So now let's look at y equals x squared minus 8. We'll do the same thing. We'll set it equal to 0 because we want to find our zeros where y is 0. And so we are going to take 8, add it to both sides, move it over here. I just flipped it because I like looking at the variables on the left-hand side. I take the square root of x and the square root of 8, so it becomes plus or minus over here. And then I have plus or minus the square root of 8. But I can simplify this radical, right? Because what is the square root of 8? It's the square root of 2 times 2 times 2. 2 times 2 is 4. 4 times 2 is 8. And I know that if I have two of the same numbers inside of a radical, I can pull that number out, right? Because I'm looking for the square root of 2. This is 2 squares, so it can come on out as a 2. So I have plus or minus 2 root 2, so I put them back in here. X plus 2 root 2, x minus 2 root 2. Boom. So now let's do this one. This one's a little bit tougher, right? So this is our first new thing that we're learning today, and it's going to be on how to, you guys might have done this before, I don't know if you have, but it's a factoring technique, so it really doesn't have anything to do with roots, but it helps us get our roots here. It's a factoring technique that you can factor something to the fourth if it has something to the second here, blank. So if you're looking at this and you're like, dang, this looks like it'd be a perfect quadratic to factor, but unfortunately where my x is supposed to be, there's an x squared, and where my x squared is supposed to be, it's an x to the fourth. Fear not, there's a tactic on how to tackle this, and it's kind of neat. It's a little neat trick. So what we're going to do is we're the gods in our math universe. So we're going to take z and we're going to set it equal to x squared, because we can do that. We can set anything we want equal to x squared. I could set a heart equal to x squared if I wanted to, and then not even have done this with a letter. I can rewrite anything as I want to. So I'm letting z equal x squared. So what does that mean? Let's find out how many x squareds are in here that we can replace with our new letter z. So we have x squared to the 2, that's x to the 4th, and then we have negative 5 x squared minus c, 14. So now let's take these x squares that I conveniently bubbled out for us in parentheses, and let's replace it by a singular letter z. So now I have z squared minus 5z minus 14. And look at that. You're like, oh my gosh, that is a quadratic. I can factor that. I can factor that because negative 7 and 2 add to give me negative 5, and they also multiply to give me negative 14. So that's what I'm going to do. I'm going to get this as my factor, my two linear factors for my new quadratic. But now I'm going to put back x squared in for my z. And it's going to go back to being, it's still two linear factors, but since it's a x to the 4th polynomial, 4th degree polynomial, I know that these can be broken up into two more linear factors, so I'm not done here. So I've got x squared back in where my z's were, and what I'm going to do is I'm just going to set them equal to 0, so I took out that step where I set them equal to 0, and I just went ahead and I added 7 to both sides to move the 7 over here. And then I took plus or minus, I took the square root of both sides, so I have plus or minus root 7, and over here I did the same thing with 2. I took it out, I set it equal to 0, and then I subtracted 2 from both sides. Now I have x is equal to plus or minus the square root of negative 2. So let's put them as linear factors, and we know how to do it. Our first one, x plus, so x plus root 7, and then x minus root 7, and then I have x plus I took out the I because it was a negative under the radical, I root 2, x minus I root 2. And I got to factor this as I factor quadratics using my neat trick where I took x squared and I let it equal to z, and then I plugged it in after I finished factoring it. Now this is on page 147. I'm going to rewrite this in terms of its linear factors. How am I going to do this? Well, this is a difference of cubes. Recall, x to the 3 and 1 are perfect cubes, and it's a difference in the middle. Remember, if this was sums, it would have to be different. If this was sums, we would do it, this would be a to the 3 plus b, and this would be a plus sign, this would be a negative sign, that would be a plus sign. Remember, because of SOAP. Remember our acronym? We reviewed this in like the first week of class. Same sign, opposite sign, always positive. So that's what I'm going to do. I find my a and my b. I take my cubed root of x to the 3 gives me x. My cubed root of 1 gives me 1. So my f of x becomes this. X minus 1, that's my a minus b, x squared, which is my a squared, plus 1 times x plus b squared. 1 squared is 1. So we have this as a one linear factor, but we see this quadratic here, and we can break this down into two further linear factors. So let's do that. Let's factor this quadratic with the quadratic formula. So I've got x equals 1 given to me by this linear factor, and then I've got this I'm going to put into the quadratic formula. So I have negative b plus or minus b squared minus 4ac under a radical over 2a. So I've got negative 1 plus or minus 1 minus 4 times 1 times 1 over 2 times 1. So if I simplify this, this is going to be 1 minus 4, so it's going to be negative 3 under a radical. I take out an I, so it'll be I3. Boom. And then this stays as negative 1, but I'm going to take the denominator and I'm going to split it up, put it with my real term and put it with my imaginary term. So now I've got negative 1/2 plus or minus I square root of 3 over 2. Perfect. So now I have three distinct factors, and I use it doing some difference of cubes. So I've got 1, then I've got negative 1/2 plus I radical 3 over 2, and then I've got negative 1/2 minus I radical 3 over 2. And I could put this back in, I'll do that here. I put it back on right here. I've got x minus 1, and then I've got x minus negative 1/2 minus all this right here. And then I've got x minus 1/2 plus all this right here. And so my last step, all I did was I just distributed the negative sign inside of my complex number. Okay, now this part is crazy and also new. So it's actually super, super neat. So complex roots and using long division. So my question is, from the Springboard textbook, page, I think 147 or 148, you'll find it. It's example D. I think it's on both pages, actually. Find all zeros of f of x is equal to this 5-term quartic, given that this complex number, 1 plus 2i, is a 0. So that's insane. I have a 4th degree polynomial where I know there's going to be 4 zeros, and I've been given 1 0. And I'm like, how can I even do that? So the complex conjugate theorem luckily tells us a second 0, which is 1 minus 2i. So 1 plus 2i, 1 minus 2i. But my degree is 4, so I need 2 more. So let's figure out how I'm going to do this. I'm going to rewrite this in terms of my linear factors. I've got this as a linear factor from here, and then I've got this as a linear factor from here. But I've got another linear factor and another linear factor that I'm missing. So for now, I'm just going to multiply these two together. So that's my step 1. Multiply these two linear factors together. Even though we don't know this one, I'm going to multiply these two together. So let's do that. X minus first complex number, x minus second complex number. So what are we going to do? We're going to do what I showed you yesterday, which was a little bit confusing for y'all, so I'm glad that we're revisiting it today. We're going to take, we're going to recognize that this expression is the resulting part of our difference of squares. So what do I mean by that? Let's look at this. Let's look at just x minus 1. Okay, so I have x minus 1. That's going to be my a. Then I have a plus sign. I'll pull down my plus sign. And then I have 2i. That is my b. Then I have x minus 1. Oh, that's my a. So I'm going to pull down my a again. And then I'm going to have my negative sign. I'm going to pull that down. And then look, I have my bi again. That is b. So I have a plus b, a minus b. And we remember, difference of sums, a squared minus b squared equals to a plus b times a minus b. So I'm now going to rewrite this with x minus 1 as my a and 2i as my b as a squared b squared. So I take my a, x minus 1 is my a, I square it, I subtract because it's the difference of squares, I take my b, 2i, I square it. Okay, so let's square these out. X minus 1 squared is x minus 1 times x minus 1. Pull down my negative sign. 2i squared is 2i times 2i. So I just simply FOIL this, x squared, negative x, negative 1 times negative 1 is positive 1. So I have negative 2x's, and then I have a positive 1. So this is a quadratic. And then over here, I'm going to take this and I'm going to multiply it out. 2 times 2 is 4. I times I is I squared. So here I've got 4i squared, which is a number. I've got a quadratic minus a number. So 4 times I squared, we know that I squared is equal to negative 1. That is a fact. I think you guys learned that in algebra 2. If you didn't, let me know, but that I feel like you should know that. So we have 4 times I squared. I squared is negative 1, so I have 4 times negative 1. What is 4 times negative 1? It is negative 4. So I've got this quadratic minus negative 4. So I can just take my constant part of my quadratic, and I'm going to subtract from it negative 4. So if I'm subtracting a negative number, I am adding 1 and 4. So I get 5. So here is my quadratic. I got this quadratic from multiplying together these two complex roots. Isn't it crazy how the complex part just disappears? I think that's so neat watching it happen. It just disappeared. It just goes away because they're complex conjugates, so they always go away. All right, so now I have this, and I have my starting equation, but I don't have this. So I have f of x, which we know is this, is equal to these things together, which I found out could also be expressed like this. But then I still have my confusing question marks, which if I had these confusing question marks, if I knew what they were, I could also similarly multiply them together like we did these two and get one quadratic. So what I've got here is my original f of x. I set it equal to my new quadratic I found, and then I have this big question mark quadratic that I don't know what it is, which is going to be a result of multiplying together these last two linear factors, which I don't know because I need to know the two last zeros. This is my original. I copied it down straight here, equals to this, which was a result of multiplying this, times my unknown linear factors, which could be represented as a quadratic in the same spirit that we represented these two as a quadratic. So I've got an equation here. I've got something equals to something times an unknown. What do? I could replace this parentheses with all these question marks as a variable. I could put in the letter, we're already using x, y, we're already using z, we used earlier, but I could put in p. I could say this is something equals something p. So what do we do to find p? We divide both sides by x squared minus 2x plus 5. We divide it by both sides. I get my unknown isolated. So to find my unknown, I have to perform this crazy long division problem. So let's get it. This is my denominator. This is my numerator. Now let's do long division, which you guys know how to do because we learned it. Okay, so quadratic and a quartic. What do we have to multiply it by? What times x squared gives me x to the fourth? It's x to the 2. X to the 2 times x to the 2 gives me x to the 4. X to the 2 times negative 2x gives me negative 2x to the 3. And then x to the 2 times positive 5 gives me positive 5x to the 2. So what do? I subtract them. This and this cancels. That's good. That's how we chose it. Now we have a negative 3 x to the 3. So we have a negative 3 minus negative 2. So that gives me a negative 1 because it's going to be negative 3 plus 2. So that's a negative 1 x to the 3. And then I have plus x squared plus 1 minus plus 5. 1 minus 5 gives me negative 4. Carry down my x squared. Alrighty, drop this down, positive 7x, drop this down, negative 30, and now I'll do the next term. I've got a negative x to the 3. What times x squared is going to give me negative x to the 3? It's negative x. If this is all like, you're like, oh my god, what? Go back and watch my videos on long division. I have the videos and you guys did delta math on them. Okay, so negative x times x squared gives me negative x to the 3. Negative x times negative 2x gives me positive 2x squared. Negative x times positive 5 gives me negative 5x. Let's subtract this one from that one. This cancels. Good. I wanted that to cancel. That's how I chose it. Negative 4 minus 2 is negative 6. 7 minus negative 5 is 7 plus 5 is 12. Drop down my negative 3 because I didn't have anything for that to combine with it. So it's really just negative 3 minus 0, negative 30, minus 0 is negative 30. So last step, I'm going to take negative 6, multiply it by x squared, gives me negative 6x squared, negative 6 negative 6 times negative 2x gives me positive 12x, and then negative 6 times positive 5 gives me negative 30. The remainder is 0. This cancels, and this cancels. How would I have already known that was going to be 0? Well, it's got a 0 remainder because the thing I was dividing it by are roots. And the remainder theorem says that if they're roots and you divide them into the function, you will get a remainder of 0. Isn't that nuts? Everything comes full circle. It's crazy. But through this process, we were able to find what our missing quadratic is. So this quadratic times this quadratic equals this quartic. So I'm going to put that back in my equation that I wrote up here in red. I've got my original quartic that I was given to in the problem. I've got my quadratic here that I found from multiplying together my complex roots that I was able to find. And then now I've got my new quadratic, which I got from using long division. I have the roots from this one already. They were these two complex numbers. But what I need to do is I need to find these two roots. So then I'll have 2 roots from here, 2 roots from here, 4 roots in total. Degree is 4. Check. So what do I have to do? Isn't it like literally so funny that this entire huge one whole paper problem comes down to just having to factor this simplest quadratic known to man? I think it's pretty funny. So I factored this quadratic. What gives me -6 when you multiply them, and then +1 when you add them? It's 2 and -3. 2 times -3 gives me -6, and then 2 added to -3 gives me -1. So here are my last 2 roots. So I have my complex root I was given, the complex root I found using the complex conjugate theorem, and then my 2 roots that I found that came down to this tiny 2-step problem that I had to first multiply together a whole bunch of complex numbers and then use polynomial long division to find. So there are my 4 roots. Alrighty, so keep on working on your paper tomorrow. You guys are going to be free all day, no Delta Math, no nothing. You guys are just going to get to work on your take-home test and your essay. Keep hitting my line with questions. If you have any, come see me in the gym. We're getting so much done. We're being so productive in there, and everybody's understanding these things so much better when they leave from when they walked in. So please come and see me in there. Also, this is the last part of learning anything about roots and anything about polynomials. Starting Friday and then the last week before exams, we are going to be learning about sequences and series, which is the actual first official pre-calculus that you're going to learn in this class. I know these theorems seem like they are, but they're actually in the Algebra 2 textbook. The regular advanced math that uses the Algebra 2 textbook and not the pre-calculus are starting it today, but they're not going into it with as nearly as much depth as we did. So yes, we're starting real pre-calculus with sequences and series on Friday, so be on the lookout for that. In the meantime, please reach out if you have any questions. Bye.